Hi, I'm Kathy Stark. In this lesson, we introduce the fundamental principle of counting, review factorial notation, and use it with two other counting methods, permutations and combinations. Let's begin with the fundamental principle. If n independent events occur with m1 ways for event 1, m2 ways for event 2, m3 ways for event 3, and so on, until we get to m sub n ways for event n to occur, then there are m1 times m2 times m3, etc., up to times m sub n different ways for n events to occur. Let's look at an example. How many different four-letter radio station call letters can be made? If the first letter must be a K or W and no letter may be repeated. If repeats are allowed but the first letter is K or W. How many of the four-letter call letters starting with K or W with no repeats end in R? Let's do this a step at a time. What we want to design are four-letter radio station call letters. First of all, how many of them have first letter K or W with no repeated letters? Since there are four letters in the radio station call letter, I'm going to put 4 spaces and figure out how many ways each item can occur. The first letter has to be a K or a W. There's 2 ways for that to occur. Now I don't want to repeat any letters. Out of the 26 letters in the alphabet, if I've put one letter first, there are 25 left for me to choose the second letter, then 24, then 23. And this product is the result. The product is 27,600 radio station call letters. Let's use that process again for part B. Again, there are 4 letters in the radio station call letter. The first letter has to be a K or a W, so there's 2 choices there. But it's okay to repeat letters in this case, so we can use any one of the 26 letters of the alphabet there, and then any one of them in the next spot, and any one of them in the next spot. This product is 35,152. There are that many ways to design the call letters in this example. Now, part C. Again, there are 4 call letters that we want to fill in. The first letter needs to be a K or a W. And I want to end in an R. That means there's one possibility for my final letter. If I don't want to repeat anything and I've put a letter in the first as well as 4th position, that means there's only 24 remaining letters to choose from here, and then 23 in the next spot. This product is 1,104. Here's an example for you to try using the fundamental principle of counting. How many different types of homes are available if a builder offers a choice of 5 basic plans, 3 roof styles, and 2 exterior finishes? Stop the tape while you work and restart it when you're ready to check. Let's see how you did. We want to know if there are 5 basic plans, 3 roof styles, and 2 exterior finishes, how many options are there? There are 3 items to choose from, any one of the 5 basic plans, any one of the 3 roof styles, and either one of the 2 exterior finishes. This product is what we're looking for. 15 times 2 is 30. Let's review factorial and then use it within our other 2 counting methods. Remember that the definition of the factorial of a natural number is as follows. For any natural number n factorial, here's the notation, is n times n minus 1, n minus 2, and so on to the integer 1. And 0 factorial is defined to be the number 1. We're going to use that within one of these 2 counting methods. The first is called a permutation, the second a combination. Now a permutation of n elements taken r at a time is a way to count elements. In a permutation, order matters. If we were counting in a permutation, we would count A, B, C as a different as a different element than B, C, A. The order matters. These two are different. In combinations of n elements taken R at a time, A, B, C, and B, C, A would be counted the same. Order doesn't matter when you're using combinations. Let's look at an example of some statements and decide if they represent permutations or combinations. What we're going to do is decide whether the situation listed describes a permutation or combination of objects. We have a telephone number, a social security number, a hand of cards in poker, a committee of politicians, or the combination on a combination lot. Let's take these one at a time. A telephone number. Now, in a permutation, the order that things are arranged matters. A telephone number is a permutation. 345 is different than 435. In a social security number, the same situation occurs. In a permutation, the order of objects represents different elements. So a social security number is a permutation also. But a hand of cards in poker, if you have 4 aces, you have 4 aces. It doesn't matter in what order they are. A hand of cards in poker is a combination. The same is true with the committee of politicians. A group of people, doesn't matter the order in which they are, if they're a committee, that would be a combination, excluding the idea of having a chair and so forth. Well, what about the combination on a lot? It makes a difference in what order you use the numbers in a combination on a lock. Order matters. That's a permutation problem. In a permutation, order matters. In a combination, we have groups of items. Well, there's 2 formulas I'm going to show you next, one for each counting method, beginning with permutations. The definition, as well as formula for calculating, of permutations of n elements taken R at a time works like this. If P of n comma R denotes the number of permutations of n elements taken R at a time, where R is less than or equal to n, then P of n R is equal to n factorial over n minus R factorial. There's that factorial notation. Let me give you the formula for combinations. Definition of combinations. If n choose R is how you read this, or C of n R represents the number of combinations of n things taken R at a time, with R less than or equal to n, then n choose R, which is equal to C of n R, is found by taking n factorial over n minus R factorial times R factorial. This extra R factorial in the denominator distinguishes this from the permutation formula. Let's try this out. Velma specializes in making different vegetable soups with carrots, celery, beans, peas, mushrooms, and potatoes. How many different soups can she make using any 4 ingredients? We need to decide if this is a permutation or a combination problem. Looking at the problem, in any particular soup, she wants 4 ingredients. It's not going to matter the order in which the ingredients are in the soup. Order doesn't matter. It's a combination problem. In addition, we have 1, 2, 3, 4, 5, 6 vegetables. We want to choose 4. This is a combination problem. Here's the formula, in which we have 6 items and we want to choose 4. That's C of 6 comma 4. In the formula, 6 factorial over 6 minus 4 factorial, 4 factorial. Simplifying by hand, I'm going to write out 6 factorial, 6 times 5 times 4 factorial, over 2 factorial, 4 factorial. Simplify the 4 factorials. 30 over 2 is 15 different kinds of soup. 15 soups. It's possible to do this calculation on a graphing calculator. Let me show you how to do that. On our graphing calculator, if we choose math, and then go over to the PRB menu, which stands for probability. The second and third options are permutations and combinations, respectively. We want to use combinations. Notice there's an N on the left and an R on the right. Before I can select that, I need to put in the number that I'm using for N. So I'm going to quit, go to home screen and put in 6. Then I'm going to go back to math, back to probability, option 3, and put a 4 as my R value. If I enter, I get the value 15. I want you to give this a try. Here's the problem. If Dwight Johnson has 8 courses to choose from, how many ways can he arrange his schedule if he must pick 4 of them? Stop the tape while you work and restart it when you're ready to check. Let's see how you did. Dwight Johnson has 8 courses, and he wants to arrange his schedule by picking 4. The order does matter, assuming that there are different times of day that the courses are offered. Since order matters, this is a permutation problem. And in this particular problem, it's a permutation of 8 things taken 4 at a time. That's 8 factorial over 8 minus 4 factorial, or 8 factorial over 4 factorial. Writing out 8 factorial, I can simplify the 4 factorial with the denominator. The final result is the number 8 times 7 times 6 times 5. That's 56 times 30. Let's get the answer on our calculator, and then we can also check this by doing a permutation on the calculator. At home screen here, I'm going to begin by doing 56 times 30, and I can keep that number on the screen while I perform the permutation. I want to put in 8, go to math, probability, option 2, and 4, and let's see if that's 1680 also. That supports our analytic work. As a final example, I want to combine permutations and combinations with the fundamental principle of counting. Let's do this. In a club with 8 men and 11 women members, how many 5-member committees can be chosen that have the following: all men, all women, 3 men and 2 women, or no more than 3 women? Since we're choosing committees, this is a combination problem to begin with. Let's do part A. We have 8 men and 11 women. We want to choose 5 members for our committee. If we want it to be all men, we want to figure out, of the 8, how many ways we can choose 5. That's a combination of 8 choose 5. In the formula, that's 8 factorial over 8 minus 5 factorial times 5 factorial. That number, if you work it out, comes out to 56, and you can verify that on a graphing calculator. What if our committees are all women? Let's take our 11 women and figure out how many 5-member committees we can make from that group. That's a combination of 11 choose 5. 11 factorial over 11 minus 5 factorial times 5 factorial, and that number is 462. Okay, let's move on to part C. What we want to do is form 5-member committees, 3 of whom are men and 2 women. This is a product of the combinations of the 8 men choose 3 times the combination of the 11 women choose 2, times using the fundamental principle of counting. The number of ways I can choose 3 men times the number of ways I can choose 2 women. Let's use our graphing calculator to find this value. On our graphing calculator, let me clear the screen. I'm going to start with 8 in math, probability, option 3, 8 choose 3, and I want to multiply that, so I'd probably better put in some parentheses. Let me go back and insert some. And go over here and times that by the number of 11, option probability 3, choose 2, close parentheses, and that number is 3,080. Let's move on to part D. In part D, we want to have no more than 3 women in our committee. That means we could have 0, 1, 2, or 3 women. The rest of the committee is made up of men, or translates to the mathematical operation addition. But first, let's figure out how many ways to have 0 women. That's a combination of 11 choose 0 women times a combination of 8 choose 5 men. We want to add to that a combination of 11 women choose 1 times a combination of 8 men choose 4, because 1 woman has been chosen. We're going to add that to a combination of 11 choose 2 times 8 choose 3. That's 2 women and 3 men. Then we're going to find a combination of 11 choose 3 times a combination of 8 choose 2. 3 women, 2 men. These numbers you can calculate on your calculator. The numbers are 56, then 770, 3,080, and 4,620. The sum of these is the answer to the question. We need to find 56 plus 770 plus 3,080, and I'm going to say or 4,620. It's the or that indicates that we add, and the result is 8,526 committees. In this lesson, we looked at the fundamental principle of counting, reviewed factorial notation, and used it with permutations and combinations. Be sure to practice by doing some of the exercises in your textbook.